these stars into galaxies. Because of this importance, people have looked into these findings, these supernovae, to understand these better. And the development of optical surveys over the past century basically have enabled a huge number of detections of these supernovae. And of course, many of them are type 1a, which are explosions of white dwarfs, but a significant fraction of these are core collapse supernovae. And another way to show this is that how the number of, this diagram of how the number of detections have evolved over the years. And since the supernova science kind of started around late 1880s, early 20th century, the number of supernovae detected has increased by a lot. And I think there are, especially for the recent few decades in the 20th century, I think there were two key progress that enabled this. And one is the development of wide field surveys around late 2000s. For instance, by Pan-STARRS and by PTF, those surveys. This basically helped find many supernovae, including the rare ones that were previously unknown, like the superluminous supernovae, those things. And in the 2010s, high cadence surveys started to develop, including ones like ZTF and many projects such as the Young Supernova Experiment. These kind of experiments basically enabled finding supernovae in days after the explosion and even within a day. And this really helped understand much deeper about the final moments of massive stars, as I'll talk later on. And the canonical understanding of these massive star explosion is basically typical cases of red supergiant, an inflated star, an evolved star that's very cool. Basically, when a supernova happens, the shock wave develops into the star, disrupting the entire star like this. And what people have thought, and what stellar evolution theory at that time told us, is that these stars lose mass by winds, but these winds are really small to really affect anything. So it's pretty much like a supernova star exploding in a vacuum. But this changed. This picture changed by these high cadence surveys that I talked about. And the representative case was by this 2013 FS, which was a vanilla red supergiant explosion, a type 2 supernova. But what was very special about this supernova was that we were very fortunate to get a very early spectra of these supernovae. So this was found 3 hours after the explosion, and the spectra was taken another 3 hours. So very early times, spectra was available for this very vanilla supernova. And what this showed is that what was remarkable was that the early spectra basically had strong narrow lines, and that faded in a very short time scale of days. And this was seen in not only H alpha, but also in helium lines as well as oxygen lines. So what this remarkable observation told us is that the red supergiant is not really exploding in a vacuum. So the existence of this narrow, strong lines indicate that there is some slowly moving matter around the star. And it has to be really dense enough to create these lines. So modeling by this paper, discovery paper of this supernova, basically concluded that you need basically confined dense circumstellar matter at a radius length scale of around 10 to the 15 to explain the very short duration of this spectral features. And what was more remarkable was that the mass loss rate inferred for this from spectral modeling basically told us that the mass required is really huge. So if you convert the density and assume a velocity and convert it to a mass loss rate, it was very large, 10 to the minus 3 solar masses per year. This is about an order 1,000 times more higher mass loss rate compared to the local red supergiant winds observed in our galaxy. And after this discovery paper, many more of these samples have been probed. And a more recent version of this by ZTF shows that it's fairly ubiquitously happening. So among the type 2 supernovae from exploding red supergiants, a majority of them tends to have this really dense matter. And if you convert that to a fraction of all core collapse supernovae, it's about 40%. So this discovery triggers some debate on how you can form these very dense circumstellar matter. And this was around the time when I started grad school, and many theories have been put out, but the theory basically was kind of split into two flavors. One is the super wind scenario, as people call it. This is basically you crank up the wind mass loss rate of red supergiant stars, maybe in the last tens to hundreds of years before core collapse. And like a varying wind mass loss rate is actually seen in AGV stars when they turn into white dwarfs. So it's a natural extension of that to the red supergiant. But the issue is that the m dot required is really huge, as you saw before. And we don't see any of these red supergiants emitting winds at that really high mass loss rate. And the other difficulty of this scenario is that this m dot is going to basically make your photosphere bigger and bigger because the wind is going to be optically thick. So it should predict a very strong reddening and obscuration in pre-supernova supergiants. And we have a handful of samples of red supergiants found before explosion, and we don't really see that reddening. So in my opinion, what people started leaning towards is that there is some unknown mechanism that ejects some mass by an eruption happening about a year, 10 years before the supernova to explain the extent and mass of the CSM. And this timescale is sort of motivated by what was already known in stellar evolution theory, where you have very late-stage nuclear burning by neon burning, oxygen burning, that's highly convective. And even if you, although most of the energy is going to be emitted by neutrinos, go away, but even if you tap a small fraction of that energy into the envelope of a massive star, you can eject it fairly well. And the other evidence supporting this scenario was that there has been discovery of precursor emission in a rare class of supernovae called type 2N. And people have speculated these things can happen maybe for the more regular red supergiants as well, but on shorter time scales compared to 2Ns. What was missing at the time was that some detailed observational predictions on how these pre-supernova eruptions would look like. And I did some analysis of how these red supergiant eruptions might look using red hydro simulations. So the game we play is pretty similar to how supernova modelers explode stars. Is that you basically take a star and you inject energy at the base. So we're agnostic to what the energy source is, but we inject energy into the base of the envelope. This basically launches a pressure wave that steepens into a shock that basically erupts part or maybe all of the star. So you can see an animation here. It went a little fast, but basically the shock travels, and around when it reaches the surface of the star, there's this initial brief shock breakout emission that is lasting for only hours to days and harder to see. But there is this long emission happening from the diffusion of photons created by this energy injection that basically lasts for a much longer time scale. And this is one realization, but what we did is to consider multiple kinds of these eruptions to see how they look as transients. So what we did is what we took is a 15 solar mass red supergiant star, typical star, and did this energy injection varying the injected energy, and varying also, and the dotted lines basically show a more aggressive way of thinking if there were two energy injections that would basically make the transient even brighter. But the main conclusion is that you basically have a brightening of the star. Go ahead.
How do you decide where to inject the energy?
Yes. Yeah, so we decided to inject at the base of the hydrogen envelope. Yeah, so these are red supergiants. They have massive, but very loosely bound hydrogen envelopes.
So you think it's like helium explosion?
Yeah, so the energy source should be somewhere much deeper inside, yes. But we're agnostic to that. And let's say some energy got traveled to the hydrogen envelope. I think it's still like a star that's at the neon burning phase. So it's not like a neutron star or a black hole has formed yet. So yeah. We're talking about the much deeper nuclear reactions happening, like the oxygen burning, neon burning. Oh yeah. So the energy injection is done at the hydrogen burning shell region. Yeah, close to the base of the envelope. Yes. Oh yeah. So the radiation hydro simulations take the diffusion into account. So we saw both the photons and gas. Yeah, that's right. Yeah. As long as we resolve that photosphere region, I think it's correctly taken into account. Although, of course, it's a 1D simulation, so multi-dimensional effects can vary, the time scale and luminosity of the initial shock breakout. Yeah, so the conclusion we got from these models we think about is that you basically get a transient that is, a couple to 10 times brighter than the initial star, order 10 to the 39 Earths per second, and it's bright in near infrared, being minus 10 mag. And the evolution is really slow because it's a fairly weaker explosion compared to like normal supernovae. So it lasts for hundreds of days. And another point we found that was kind of interesting is that the main peak is, we think it is powered by hydrogen recombination. So basically when the ionized part of the envelope gets ejected, it cools down and hydrogen recombines. So you get 13.6 electron volts from each recombination of hydrogen. And this energy is order 10 to the 47 Earths. And that's unimportant for supernova explosions because those are really more energetic, 10 to the 51 Earths. But for these weak explosions, the recombination of hydrogen actually plays a big role, powering the light curve over this time scale and this luminosity. Okay, so with this model in mind, we were thinking, okay, how can we test this with the observational capabilities that we have? So here's a plot showing that how the magnitude will be as a function of distance, and compare that to the supernova rate. So if you look at the radar filters of ZTF and LSST, ZTF is going to be fairly shallower than LSST, so you can basically distinguish these scenarios up for really nearby supernovae up to like 5 to 10 megaparsecs. So looking at this, I was a little pessimistic, saying that we will probably have to wait for LSST to really test this scenario, because the event rate of supernova, red supergiant explosion, is pretty rare until you get to like 10 megaparsecs. So my hope was that the Rubin Observatory, when LSST starts, we can really distinguish this phenomena, whether this is actually happening or not. That was betrayed in a good way. So 3 months after this paper was published, there was a really nearby supernova that happened. It's called supernova 2023 IXF. It's happened in a galaxy called the Pinwheel Galaxy. You can see the beautiful spiral that looks like a pinwheel. This supernova showed similar spectral features to how I talked about, where the very early spectra up to days after the explosion showed narrow lines that indicate slow dense material around the red supergiant. And what was remarkable about this supernova is that because it's so nearby, there are a lot of observations of this galaxy, and including the progenitor red supergiant. So we had a whole lot of data about this progenitor star that we can now start testing the scenarios that I raised before. And this is the work done by Izudong sitting there. And also people in Ashley's group also did a follow-up study with more wavelength coverage. What they find is pretty remarkable, a pretty stringent limit across a very long time scale, basically. So the observations span from almost 10 years before the supernova to really close, like maybe months before the supernova. And I try my best to overlay it with the prediction that I have here. It's an infrared band, so it's not a apples to apples comparison, but you can see that it's really hard to fit this transient into this upper limits. So the basic conclusion from these observational studies found that this isn't really a viable solution to explain the dense circumstellar matter. So long story short, basically Izu killed my favorite prediction, favorite model, but we're still good friends because that's how science progresses, and I'm happy I was able to contribute to this in an unexpected way. So now the community is shifting towards basically how you make these dense circumstellar matter by an eruption-less scenario. So one of the scenarios that Jim Fuller and I worked out while I was in Caltech is when we think about red supergiants, they have a really convective envelope, and the convective speeds is order like 10 kilometers per second in the near surface. So in the near surface, these convective motions can be almost transonic or even supersonic. So you can basically launch shocks that drive some matter, lift some matter up from the stellar surface to what we call it as a chromosphere. And this basically creates some dense pile of matter that part of it falls back to the star, but there is this boil off always happening, that some of them will accumulate really close to the surface, and some fraction of them will expand large enough that it would form dust and be ejected as a wind. So we built this scenario that basically captures the wind mass loss rate seen in red supergiants fairly well. But that led to also a prediction that you will have a very dense circumstellar matter naturally by this mechanism. And the density of these material would be a strong function of how strong the convection is in the star. The other scenario, more recent scenario that people start to discuss is these red supergiants can have very large amplitude pulsations, similar to AGV stars. And recent models using like stellar evolution called MESA find that these stars can pulsate really a great degree, about a factor of 2 in radius, and we're not sure if this is a real feature. I mean, there are uncertainties in the stellar evolution part that can affect how convection and pulsation proceeds in the surface. But this is a promising possibility to say that you would occasionally have very dense material outside the star that can potentially be an explanation for the dense CSM seen in these supernova. Yes? Oh yeah, yeah, there can be mass transfer. I think this is a viable scenario. The difficulty there is how you get it really close to the star. Because these stellar evolution basically, the envelope basically stops expanding 1,000 years before core collapse. So the mass outflow will be happening for 1,000 years. And you would have a CSM that is pretty large radius compared to what is observed. So it's pretty difficult to tune the binary interaction to just before core collapse, is my opinion. Yeah. Yeah. Yeah, so they claim that this pulsation will basically change the amplitude you see in the infrared that can potentially explain the pulsation seen in 2023 XF. We don't, but this pulsation basically comes for free. Yeah, we don't include it in the model, but there can be some pulsation basically changing the radii of the star that can change how much mass is basically being accumulated and how much being ejected. Okay, so this is a current theoretical status about red supergiants. But I talked a little bit a while ago about we do see these precursors in a fraction of the supernovae in called type 2n. And I didn't give an answer to this question yet because it's a really difficult question. So the observed precursors are shown in basically the left half of this plot. So you see the supernova, and occasionally when people look at archival data from these optical surveys, they find these quite bright flares spanning from around 10 to the 6 to 10 to the 8 solar luminosity. And this brightness is quite strange. So when we looked into eruption models, like how I explained, the luminosity is order 10 to the 6 or less. So it's really hard to reproduce these really bright flares. And the argument basically comes from the fact that if you want to eject a fraction of the envelope, not the entire envelope, you would basically end up with an ejecta that's order the escape velocity of the star. And when we do the math, it turns out that the radiation that can come out from this ejection of mass is going to be capped by the Eddington limit, or maybe a factor few times the Eddington limit of massive stars. So, but the observed ones are basically 10 to 1,000 times the Eddington limit, which is why we're not really able to explain these really bright flares in these stars. So the question really boils down to how to power this emission that's way brighter than the Eddington limit massive stars without destroying the whole star. Of course, like if you consider a supernova explosion, that's way brighter than Eddington. So you can, if you take the option to blow up the whole star, you can get way brighter emission. But that's before blowing up the whole star. So how do we do this? And this is a difficult question, but this is one scenario that we came up with. So we consider a binary system, like I said. But we consider a system where the companion is a compact object. And what we think is that, okay, for these events with precursors, might have had an outburst that ejects mass. That creates a CSM around this that expands over time. So once the CSM expands enough, that some of the mass can be captured by the compact object, you can get basically accretion onto this compact object. And you can use this accretion energy to boost the energy budget of the precursor. And when we do a simple Bondi estimate of how much mass can be captured, it's quite huge. Like the Eddington limit, it's going to be orders of magnitude higher than the Eddington limit. So, and this is, of course, depends on the mass of the CSM, more mass, more accretion. And also the binary separation. So it requires it to be a fairly close binary. But if that kind of system is realized, you can have strong accretion onto the compact object. And super Eddington accretion results what we call outflows that can basically inject energy into the CSM. And if that energy is efficiently radiated, we can see the emission being much brighter. That's the idea. Okay, so this is the only equation in this talk, but we basically built a light curve model to try to capture this effect. And of course, there are a lot of uncertainties in one-zone modeling, of course, but we take the simplest approach as a proof of concept. So this equation is basically the first law of thermodynamics, saying that the internal energy in the CSM is governed by the expansion, so the PdV work, and the energy injection of this wind into the CSM that will be dissipated and turn into internal energy. And the most importantly, the photon diffusion through the CSM, which basically sets the light curve. So we do have some assumptions on how the energy is injected by this accretion, which is probably the biggest uncertainty in this model. But we assume that the boundary accretion of CSM by the neutron star or black hole. And since the accretion is super Eddington, we take a very simple phenomenological model of how the outflow will scale with the mass, the accretion rate. Okay, so using this model, we can basically construct light curves of these binary energy injection by a binary system involving a neutron star or black hole. So here's one case of let's say you have a 10 solar mass red supergiant and a 10 solar mass black hole, and you eject some mass as CSM, and basically the different lines are varying the mass of the CSM as well as the separation. So these two parameters play a key role. And at the initial phase, when the CSM is still expanding and not within the influential radius of the black hole, you basically have this very dim transient, as I talked before. which is going to be capped by the Eddington limit. But once the CSM expands, and you can have energy injection by this accretion, you basically have a much brighter transient after all. So the separation basically dictates when this accretion starts, and also how much mass can be accreted. So a wider separation results, so if you look at the orange compared to the blue, the wider separation results in a fainter and transient that peaks later. And if you raise the CSM mass, you basically have more stuff to accrete, so you basically boost the energy budget. But the diffusion will take longer time due to the higher mass. So you basically have a longer rising, brighter transient. Yes?
You expect this accretion injection energy to come out with a different spectrum? Assuming it will all be the same spectrum?
Yeah, so we assume that basically the energy being injected is completely thermalized in the CSM. So that's the assumption here. And if the energy, if it can be, the outflow can break out of the CSM, for instance, by either a jet or a very fast wind, then you might see a different spectra depending on the viewing angle.
Yeah, that's exactly what I'm thinking.
Yeah.
See variability because there will be the period of this black hole star around the star, right? So we will see every period you will see an enhancement in brightness.
Well, you basically have a black hole orbiting and carving the CSM at all times.
No, but depends on the viewing angle.
Oh, yeah.
What are you assuming what you're doing?
So it's a one-zone model, so we don't take into account any asymmetry.
You will see some variability. There is no way to escape it. Unless you are somehow in the pole.
Yeah. I think that makes sense.
You
Yeah.
will see variability.
I think we don't really have strong conclusions on that.
Period.
The period is, for a red supergiant, it's going to be really long, like order of years. So it's probably not going to be visible in the spectrum. But if you think like strip stars in closed binaries, that can have detectable variability, as you say, because the orbital period is going to be much shorter, like days to maybe a week. Okay, so now we compare this model to the observed precursors. And basically there is a freedom of when this explosion happens, so you can shift time in horizontally. But this simple model fairly captures how the precursor evolves in time pretty well. Yeah. Okay, so we can basically play the same game, varying the parameters that really influence the light curves, which is the mass of the CSM and the separation of the two stars. So what we find is that you can basically predict a very broad range of luminosities and a narrower but still broad range of duration. So like as I explained, the mass of the CSM basically dictates the brightness and the duration of the flares, whereas the separation sets how long this accretion phase lasts, as well as its brightness. So if you overplot with the detected precursors, it's basically up here. And the implications we get from this is that, yeah, we have the things that we're seeing is probably the brightest ones. And if the model is correct, there should be a lot fainter precursors of order 10 to 40 or lower that we don't see it just because we're not sensitive enough. So I think this is one thing that can be tested by Rubin, is because these are way more sensitive surveys. And yeah, we'll see. And another implication that I personally think is interesting is that these red supergiant compact object binaries are basically non-interacting binaries until this mass ejection happened. So So if you think, what was it like before? It was basically a massive main sequence star and a compact object companion. And if you assume that the orbit separation is fixed, then you get an orbital period of years to explain these precursors. So what we think is that this is testable by astrometric satellites like Gaia, which basically has in this next DR4 release a 2,000-day baseline of data that will be sensitive to these massive star binaries. Okay, so we have a model of this that fairly works, and I was happy. Yeah, go ahead. Yeah. That's right, yeah.
It's a very, like, statistically, this would be a very, would it explain the whole population of these high luminosity objects we see, or because I think it looks like that, yeah, it requires very specific conditions.
Right, so yeah, a concrete prediction would require like binary modeling, of course, but the numbers I get here is basically comes from the event rate of these observed precursors, which is like 1% of core collapse supernovae. And yeah, so this comes from basically massive star lifetime of 10 to 7 years, core collapse supernova rate 1 per 100 years, times 1% of being precursors. So. Sure.
Is in the last few thousand years or so, or
yeah, or more like a few years too, because we see the precursors like order a year before. So yeah, there is an unknown fraction of how many of these stars would actually have these outbursts we do before, and we've seen that 23IXF wasn't the case. So that is a major uncertainty in the model, I think here. But yeah, this is so far the only model really proposed to try to explain these precursors. So yeah, be good to come up with more models or try to figure out a way to test these scenarios using like other probes like Gaia. Okay, so I was happy getting this model to fairly work for the observed precursors. But Itsu again came along and said, we found something interesting. So there is this supernova called 2023 FYQ. This supernova had a very long rising precursor of 1,000 days or more. So here there are many upper limits, but if you stack them, you end up with a couple detections. And this already tells you that you need to have this like really long time scale evolution that goes from a sort of more or less steady phase to a ramp up until you get the supernova. This is very weird. And this is weird because in the previous models I mentioned, the time scale basically comes from the diffusion time scale of the CSM. So if you plug in the numbers, you get a fairly short time scale for a reasonable mass and velocity of the CSM that can explain this. And if you want to explain a 1,000-day rise, you basically need a CSM of 1,000 solar masses, which is a little weird. So this tells us that it's not really the photon diffusion time that's governing this evolution in the light curve. So it's not like a one-off eruption that I just talked. There has to be something more continuous eruption that evolves on this time scale. Yes?
So where is the eddy? Is most of this about eddy?
So here is about 10 to 40 ergs per
most
second.
of that,
So that's already 10 times 10 of massive
already
stars.
there. For a year it kept going
Yeah.
higher and higher.
Yeah.
What is it, exponential or
I think it's super exponential.
super exponential? Well,
If I know what that means. Yeah. Yeah. So this kind of tells us that this scenario doesn't really work, and we really need something that is basically injecting energy at basically this kind of evolution to explain the light curve. So what we noticed after a couple of days of thought is that we actually see this light curve for a similar transient called a luminous red novae. It's similar except that it's 1,000,000 times fainter than the supernova that we see. But the light curve evolution is basically similar. And for luminous red novae, the origin is fairly established, at least for the binary systems that we know in the Milky Way, is that basically you have this unstable mass transfer that undergoes a runaway at some point and leads to a merger. So this is for a famous event, V109 Scorpii, that we have a detection of an eclipsing binary at this really fairly steady state phase. And then we find that this unstable mass transfer scenario fairly matches how this light curve evolves over time. So this is the work by Morgan, McLeod, and Javi, and Andre Peja, and others. So we saw that an analogy can be applied for the precursors that we observe, but the problem is that it's much brighter than luminous red novae. So the scenario we saw is pretty similar to what I talked before, is that you basically consider a compact object companion, either a neutron star or black hole, that undergoes unstable mass transfer, leads to merger. And here we think that the power source basically comes from the accretion, again, the super Eddington accretion onto the compact object. So we've built a light curve model again for this. So we considered the unstable mass transfer leading to merger that basically gives you a prediction for how much mass is transferred as a function of time. You basically feed that to the black hole and do a similar game as before to consider how much energy will be deposited into the precursor emission. So the light curve model that I constructed worked fairly well. So we considered the first model that I tried and worked. So I think I can trust this a little more than the other models I proposed. But for this specific event, which was a type 1bn supernova, we consider the most likely scenario progenitor to be a low mass helium star with a compact object, probably a neutron star companion, because the long time scale requires the orbit to be fairly wide and the star to be puffed up. And low mass helium stars can do that. Okay, so there has been radio follow-up of this supernova, which was published the end of last year. And the predictions for the mass transfer rate we get basically gives you a CSM density profile because you know how much mass is being ejected. You need to have some assumption on the velocity, which is in the model. But the CSM that we predict seems to fairly well reproduce the late time radio detection on these supernova. So that's another thing that made me like this scenario. Okay, so in the future, we will have Rubin very soon. So the Rubin Observatory is already operating, and the actual survey is going to start very soon. So what Rubin is really good at is to find these dim sources because they are 100 times sensitive than existing wide field surveys like ZTF. And they are very good at finding rare sources because it's basically a nearly all sky survey. So Izu made this nice plot that you basically can detect all these precursors fairly easily by LSST. And for relatively nearby events, that's about 100 megaparsecs. So you can find these supernova at precursors, like when the precursor is actually happening. And that's really a breakthrough because previous surveys basically found it based on archival data. So you basically have the supernova happen already. And then you look back into the data and you find something. But now, since we can find these precursors when it's already happening, that basically enables you to take spectra, for instance, and understand it way better than just the photometry. Okay, and there are many optimistic predictions on how many precursors we can detect, and we think we can detect hundreds of these per year, which is quite encouraging. What's that? Sorry.
Almost every day we have something to come.
Oh yeah. Or easy to analyze. Okay, so we're trying to be prepared for this era to come. So as I said, we will plan to have real-time precursor follow-up using optical spectral observation, as well as, if we can, JWST, for instance, to really probe into the infrared as well. And on the theoretical side, I think there are many things we can do. One thing is what we're doing with Morgan and Ashley is we're trying to build a semi-analytical model templates of these, so that when we have a precursor every day, we can try to fit a light curve with our model to constrain how much, for instance, how much mass is being transferred at a function of time. That can tell you a lot about what the progenitor system of this precursor would be if you assume it's a binary. And also, we have Samuel Fien over there who's working on forward modeling using binary models created by Mesa, and combining that with Morgan's model on how the mass transfer rate evolves as a function of time until merger, so that we can make reliable light curves of how these precursors will be, and can make forecasts for how much Rubin will find these binary mergers. Okay, so that is all. So the take-home message is that there are puzzles on how the last moments of massive stars are, and we are gradually making progress on trying to understand the diversity of these last moments of massive stars, as well as how they look in optical and near future surveys. And I think Rubin will be a game changer, and it's very fortunate to be here at this time, such that there are wonderful colleagues to work with on this. So yeah, that's all. Thank you so much.
Okay. We have a few minutes for questions, if anyone has any questions.
Yeah. Please.
Thanks for the great talk. I see you have so much work to do, and I'm going to bother you with another work question if you're considerate. So, this mass loss scheme of, you mentioned an important point about these convective envelopes, the convection is supersonic, and this could lead to some pulsation-like mass loss. Have you thought about just extending the mass range to maybe 50, 60 solar mass stars? I know you have a lot to do, but these stars would be close to the Eddington limit, so the radiation pressure could lead to more mass loss theoretically from the stellar evolution side of things. So I'm just wondering, because we also are trying to figure out this mass loss prescription at the end of main sequence, and we are completely hitting the wall. We don't know.
Yeah, I totally understand the current, progress on this. That it's basically entering the LVB regime, so things are more uncertain theoretically and observationally. So yeah, our red supergiant models are basically, works for things that become red supergiants, unlike luminous blue variables. And what we find is that around 20 solar masses or more, these stars basically shed all the hydrogen envelopes before core collapse. So they will become strip stars rather than red supergiants. Yeah, and I think if you basically increase the mass, you would basically have this strip star enter much earlier in evolution. That's my expectation.
And also, just sorry, quickly about this wonderful way how you inject energy into in the beginning when you spoke. So you inject it somewhere in the envelope of the star. Would this same idea theoretically could be applied to, again, these 50, 100 solar mass stars at lower metallicity, where, let's say, there's less line-driven mass loss, so we retain the envelope, theoretically speaking. Can we explode these stars using your...
Yeah. Totally possible. Yeah, I mean, of course, how you get this energy is uncertain, and these stars would have much larger binding energies, so the required energy to inject anything would be more strict. But yeah, if you have ideas on how you can inject energy into these massive stars, it's
I'll follow you later with this. Thank you, this is great.
Yeah.
Thanks.
Thank you.
All right, any other questions?
Yeah, so one thing to recognize is with LSST, you will have a problem of riches in the sense that these are the kind of things we are thinking about, but there will be many more. And in fact, the question is, what is the most abundant type of transients on this time scale of this amplitude? And so the problem might be to separate those that you care about from the many more that are for other reasons. And there might be unknown populations, and I don't know how you will cope with that, but maybe with AI.
Yeah, I mean, I'm interested in all transients, so that's fine. But I think the really important thing is spectra, I think. So in this probably luminosity and duration range, there can be like luminous red novae or something that's somewhat fainter than supernovae, like maybe black hole formation, for instance. So distinguishing these probably require to take spectra that will constrain basically what kind of star is participating. Is it a hydrogen-rich star? Is it a strip star? And the kinematics of whatever outflow is being ejected. That can also tell you what the progenitor would be, so that we can constrain these channels a little better.
Okay, any other questions?
If you replace the black hole or neutron star with a white dwarf, do you get a type 1a with a big CSM?
Oh, that's a good question. I think in principle you can. There is a subclass of 1As called type 1A CSM supernovae. It's really a jargon, but there are like supernovae that show 1A like spectra like times, but early times you see this very dense CSM that I talked about. So in principle, I think it can explain. The bigger issue is I think how you form the white dwarf first, because you have a massive star and then a white dwarf, but the massive star naively should evolve first to become a neutron star or a black hole. So yeah.
I was thinking of a helium star and a white dwarf.
Oh yeah, I think the rates are probably lower, but I think those systems can indeed exist. And yeah, I mean, it's hard to kind of say how much of that CSM would accrete to the white dwarf, whether it would have enough mass to exceed the Chandrasekhar limit, for instance. But yeah, I think that's an interesting possibility to think about.
Okay, we have time for one more question, if anyone has any. I might ask a question. Oh, sorry, Isa, do you want to ask something?
So I guess with Rubin, we have found more precursors. So would you think it will be possible to predict when supernovae will explode, and what features can we use to do that?
Yeah, so I think if you just look at this really steady phase, I think it's hard. But if you can find any variability, like a rise in the light curve. That's when we can probably start saying roughly when we might expect the supernova to happen. Yeah, but I think more effort is needed on that, including the light curve modeling that we're trying to do. You had a question?
Oh, yeah. Oh, I guess I can ask it now. Okay, so I guess I'm wondering, with your like years-long precursor binary merger model, I don't know if we have like a rate estimate of those precursors, but does it match the rate of binaries? And like, is there any other emission or properties that we would expect those mergers to have that might help us distinguish them?
Right. So for the supernova that I talked about, it's a type 1BN supernova. There's a handful of these 1BNs detected at similar distances, and then this only one has this long rising precursor. So we know the rate fairly well, like probably a fraction of 1BNs would do this. And I think this can be explained probably because, you know, a companion can be either a main sequence star or a compact object to produce the same rates, but the fraction of these being compact objects is going to be lower than it being a main sequence star. So yeah, I think that kind of binary model probably works to explain the relative rates of these.
All right. I think we have to end now, but if you want to talk to Daichi more, he has a schedule and I think a few more open slots. But let's give one more round of applause.
Around for maybe one year or 2 years.
Yeah. So find him. All right.
Thank you.
Thank you.
It was excellent, very stimulating. Good luck in that.